Hey, here we are, ready for another one of our little tabletop experiments. In this case, we're going to find out about something called enthalpy of solution, the change in energy as a substance dissolves. And we'll figure it out per mole, of course. We have some interesting equipment I'll be using here. First is one of my favorites. This is one of the reasons I got into chemistry, because of these little toys. This is a stir plate. There is a magnet underneath this piece of glass and a little motor with a speed control that spins that little magnet. And here I've got a piece of Teflon, a Teflon coated magnet, and of course they'll be attracted to one another. And when you turn this, your little magnet stirs. This is a stir bar. The Teflon doesn't react with anything. So this is so neat because you don't have to do any stirring, which I would normally have to do for this experiment. So let me turn this off right now and I can play with it another time. I'll take this Teflon stir bar. These things disappear very quickly, so I'll make sure I don't lose it. The other thing that we've got is a probe rather than a digital thermometer, but it's hooked up to my calculator. And this little deal is really, really slick. It's basically a digital thermometer, but this will allow me to graph things. And all I have to do is turn the darn thing on. And it has a built-in program by Vernier, which does a lot of stuff. There we go. Vernier Easy Data, where you can collect all sorts of data depending on the input of the probe that you have. In this case, we've got ourselves here we go, a digital thermometer, and we can have it. Let's see if I can warm this thing up. Ah, yes, indeed. Okay, we're set up, and I've got this all arranged. Of course, I've got my styrofoam cup, which is going to be my calorimeter. The heat of solution for is an ionic solid. Its common name is Epsom salt, named after a town south of London, where back in 1698 they ended up digging a well and found out that the water was pretty bitter. But if you drank the water, it had medicinal effects. It ended up clearing out people, as it was a natural laxative, and people would go there regularly for their spas to get cleaned out. And they still sell Epsom salts as a laxative. As you can see here, I've got this, and it's listed as being USP, which is certified for drug use. So you could take this mineral, which the Epsom spring that they used as a spa has dried up since, but now they mine it and get it quite pure. And people also will use it as a soaking salt. In fact, in high enough concentrations, you can float in it and have a neutral buoyancy bath, which is what it's used for also. I've taken that Epsom salt, and it comes in pretty big crystals and chunks, and I ground it up using my little mortar and pestle. So I've got a whole bunch of very finely ground Epsom salt so that it'll dissolve quickly, because I want it to dissolve in the water and see what happens to the temperature of the solution in the dissolving process. That's the enthalpy of solution. All right, now I'm going to figure out all the data that I need for this, and the first thing is I'll need my mass of magnesium sulfate. By the way, this is a hydrate. It's got water crystals locked into it with covalent bonds. The magnesium which has the positive charge. The magnesium ions have the oxygen part of the molecules attracted to it. And I've got my ground up magnesium salt, and I'm going to get my balance going. And I'm going to weigh it on my slick weighing paper here. I've got some blank one here. And I'll tear this out and get my mass. I'll pour the amount that I'm going to be using. This is, I think, going to be around 14 grams. And get it onto my weighing paper so I can transfer it into the solution quickly and easily. Oh yeah, okay, there we go. 14.56 grams. You got to write this stuff down as you do it. I mean, it'd be horrible doing an experiment and then saying, oh, I didn't measure that. I'm out of luck. So it's pretty stable at 14.5655 grams. It's staying at 6, so I'll do 14.56 grams of my magnesium sulfate heptahydrate. Hepta would be 7 water molecules for every 1 formula unit of magnesium sulfate. I'll put this to the side very carefully so I don't lose any of it. And next, I will end up needing to get my mass of my empty calorimeter that I'm going to use to do everything in. And I've got, you can hear it, my little, let me pull it out, a tinier stir bar. And there we go. Let me get that mass of the empty calorimeter and stir bar. I'll zero out the balance again. And give it a second to stabilize. I don't have a draft shield, so just a little bit of air, is going to affect things by a 100th of a gram, a centigram. I'll zero it again and see if we can get there we got a stable 0, and find out the mass of my empty calorimeter is nice and light. One of the things about foam polystyrene, it is light, 8.45 grams. Okay, so there we go. Now I'm going to put some water in here. Now I've pre-measured the water out in terms of volume. I've got about 70 mLs, but I'm not really going to bother weighing things right now because I'm going to be more concerned about the solution. So I'm going to add my water in here, room temperature, pure water, and get my calorimeter onto my little stir plate, get things stirring a bit. I'm checking the stir bar. Oh yeah, it's spinning nicely. I'm going to immerse my thermometer in there because I'm going to need a temperature 1. And I'm not going to have it knocked around by my thermometer. And I'll get it spinning just a little bit more. Get a little vortex going. And we'll find out what our temperature is. We'll let it stabilize. It's dropping a bit. Looks like we're going to be at 17.8. Yeah, it's sticking at 17.8 for us. And I'll write that down as my initial temperature. So we're moving along nicely on this. Staying at 17.8 as temperature 1 of the water. 17.8 degrees Celsius. Yep, staying constant. Very, very good. And now let's dump that Epsom salts in there and see what happens. In fact, actually what I'll do is I'm going to graph what happens. There's a function here which is nice that allows you to graph the temperature as you're going, and I'm going to start it right now. Okay, come on, graph. Okay. What we'll do is we'll start. That's what we need to do. Start. And there we go. We're graphing 17.8. And I'll get my little weighing paper. I got to be careful not to lose this carefully weighed stuff. Magnesium sulfate heptahydrate. And we'll see what happens when this stuff ionizes into aqueous magnesium ions and aqueous sulfate ions. Temperatures staying dead rock constant, and now let's dump our magnesium sulfate in there. And we'll get the stir bar stirring. I've got everything out there, every grain that's in there, and we'll see if anything happens to the temperature as this magnesium sulfate starts to dissolve. And oops, let me get it going a little bit more. Oh, temperature's dropping. We're getting a temperature now down to 16.4, 16.3. Let's keep on going. Let's really get this stuff dissolved as fast as we can. 16.1. So the temperature is dropping. We're down to 16, 15.9. Our temperature is decreasing, and that means that this is an endothermic reaction. The bonds of the magnesium sulfate heptahydrate, all locked together, are being broken, and new bonds are being formed with the water in the aqueous form. And those new bonds must be weaker because as those new bonds, aqueous bonds, form, we're not getting as much heat back as is being used to break up the magnesium sulfate heptahydrate. And we're still dropping our temperature down to 15.2. And again, we'll stir it a little bit faster, making sure all that magnesium sulfate ends up dissolving. 15.1. Temperature is continuing to drop. So we'll wait until it restabilizes again. And it looks like 15.1 might be, oh no, we're down to 15. I'm going to take a quick look inside, and I'm still seeing a little bit of cloudiness. And right now we're staying pretty much at 15. So we're having about a 3-degree drop for 70, well, I have about 70 mLs of water, but we'll see. Nope, it's staying. And let me see if that stuff still stays. Looks clear. Yeah, the solution in there looks just like water right now. So, oh, there's our graph. We can see the temperature is dropping, and it stopped at 3 minutes, so I'm going to have to, in fact, here we can see we had a drop, and now it flattened out, and we ran out of time. This thing will only graph so much, so I'm going to switch over to main, and see that our temperature is 15. We've pretty much established ourselves as 15. Looks like everything is dissolved, so we now have a temperature 15 degrees. We've dropped about 2.8 degrees. Not much of a temperature change, so we're going to be, our final data is going to be no better than 2 significant digits, and considering that we only had a drop of about 3, just a 1/10 of a degree error is going to mean that we've got 1/10 out of 30. We can have, an error in the area of 3 or 4% natural. I mean, it's just changing the temperature by 1 degree, but this is looking nice and rock steady at 15. So even though we add a small temperature change, we can be pretty certain of what happened. So let me stop the calorimeter, stir bar, and now comes the critical part, because we need to know what changed temperature. The important thing is the solution. The solution started off, both the magnesium sulfate and the water, at our 17.8 degrees Celsius was the initial temperature. And now we've got our temperature down to 15.0, and we need to know what material. In fact, we'll assume that this solution has the same temperature, same specific heat as water. It's pretty dilute. It's not really a concentrated solution, so that's not a bad assumption. Ooh, right now the temperature is dropping, but that's because the thermistor has water on it, and that water is evaporating. That's interesting. Okay, so in fact, when the water evaporates, the water molecules have got their bonds broken, and that's it. We're seeing the endothermic reaction there. So I've got the balance zeroed. Let's find out the new mass of solution and calorimeter as being 93.73 grams. We'll be able to subtract and find the mass of solution. We're going to presume the specific heat, and we'll be able to find the joules of energy that were absorbed to make weaker bonds, to make something with a higher amount of enthalpy. This is going to be an endothermic reaction of plus delta H. So now it's time to do the calculations to calculate the enthalpy of solution. You're going to have to calculate Q first, which is the heat that changed in the calorimeter. Assume that the heat of the reaction is opposite that, negative Q, and then use the number of moles of the Epsom salts, the magnesium sulfate heptahydrate, to find out how much heat would have changed and how the enthalpy would have changed per 1 entire mole of this Epsom salt. So let's get that done. Okay, welcome to part 2. In the first part of the experiment, I dissolved some magnesium sulfate heptahydrate in water, and we found the change in energy, and I was using a stir plate with it. And you didn't get a chance to see the stir plate in action because I was using a calorimeter. You couldn't see it working. But here it is. Here's that stir plate stirring some water, making a beautiful vortex. I mean, being able to use stir plates is enough to make you want to major in chemistry just all by itself. But chemical reactions are what are really interesting in chemistry. So I'm going to stop this and we're going to look at this reaction. In the previous experiment, we made some sodium acetate by taking acetic acid, vinegar, and neutralizing it with sodium hydrogen carbonate. And we had one of our products was sodium acetate in addition to water and CO2. I took that solution that we had, that neutralized solution with sodium acetate, and let it evaporate. And you can see that we have some beautiful crystals of solid sodium acetate. Now that sodium acetate is a dihydrate. It's got a little bit of water in its crystal structure. And I put some of that sodium acetate. Here's a whole bunch of sodium acetate. And as you can see, it's a solid at room temperature with this water of hydration. And I have it here. Now, you can warm sodium acetate up, and as many ionic substances are, it becomes more soluble in hot water than it is in cold. And I'm going to take some boiling hot water and use that as a water bath. Here we go. I'll put this in here. And I've got some water I just boiled up. And I'm going to use that as my water bath. You can see it's steaming hot. I've got enough there so that you can see what's happening to the sodium acetate. The hot water bath, let me check the temperature of that bath. Get my thermometer out, and we're dealing with water that's 75, 77, 78 degrees Celsius. And right now you can see that clear layer. That's where some of that sodium acetate is dissolving. And we'll let this go for a few minutes, and I'll put it on time lapse. You maybe see me refill the water every once in a while on this the hot water bath. Make sure it stays hot enough, and you'll be able to see this sodium acetate dissolve in its own water of hydration, and we'll have a solution, a very, very, very concentrated solution of sodium acetate in a few minutes. So we'll let it just go, and I'll fast forward this for Okay, it's been a few minutes, and you can see through the fast forward that the sodium acetate has dissolved in its own water of solution. So we now have a very, very concentrated solution of sodium acetate, and it's only able to be this concentrated because it's at a pretty high temperature. If it's at the same temperature that the water bath is at, we're dealing with like stabilizing at about 68 degrees Celsius, scalding. And I'm going to reverse that right now by getting rid of this hot water bath. There we go. Ooh, that is hot. And switching over to an ice bath. You can see there's some ice cubes in there. And with those ice cubes, if this is properly mixed, we've got a 0 degrees Celsius from 60 to 0, quite a shock. And we'll give it a few minutes and let it cool down to whatever the temperature of that ice bath is. And again, we'll time lapse this to make sure that this gets down to at least room temperature before where it was a solid. And so let's let time do its thing. We'll see if patience is a virtue. Alexa, stop.
5-minute timer stopped on Mary's Alexa app for PC.
Okay, we've had our 5 minutes for this to cool, and let's bring this down so you can see our solution. And even though it's cooled to where it should be solid, where the temperature is such that this much sodium acetate can't dissolve with this amount of water, it's still in solution. This is what's referred to as supersaturation. In the solution itself, it would naturally be a solid, but right now it's not. For some reason, it's not. And these supersaturated solutions are very interesting. And I'm going to turn on our digital thermometer and get our Vernier Data going. And what I'm going to do is take the probe, which has a little bit of crystal, sodium acetate crystal on it. You can see I have some on there. And I'm going to immerse it into the supersaturated solution. Supersaturated solutions will will end up recrystallizing if they have an impetus. Like, for example, if I shook this, it would end up somehow, there'd be a correct arrangement, and the sodium acetate crystals would end up forming a solid, in effect coming out of solution. Now, in order for it to dissolve, it was an endothermic reaction. Now we're going to end up doing exactly the opposite. We're going to have it undissolve. Now, the temperature of that acetate right now is probably less than 18.8 degrees. You can see via the digital thermometer. Let's see what happens when it undissolves. So I'll grab that probe and just insert it. Wow, look at that, instantly. And our temperature is going up to, wow, 18.8, 18.9, 19, 20, and the temperature is 20.2, 20.7, 20.9. This is an exothermic reaction at 22 now, 22.3, as the stronger bonds form when the crystal lattice snaps together, making stronger bonds, releasing kinetic energy as it loses potential energy. You can see this drop in potential energy. This this solution was ready to form stronger bonds, and now it's done it. And it's done warm right now. We're up to 26.4, and we were at 18 before. And this is, this makes sense. If dissolving this substance is endothermic, undissolving, which because you're breaking bonds, you're making weaker bonds than were there originally. If you go backwards in time, or backwards, and make stronger bonds as it recrystallizes, you should end up losing that potential energy as it changes into kinetic. And there we go. There's our kinetic energy. We're at 28.1 degrees. Sometimes you'll see this experiment done on the internet and refer to the stuff as hot ice, where they'll take this solution, clear solution, and poured out, and it instantly crystallizes and it generates heat. Well, it's not hot ice. It's a undissolving reaction that you saw here that's now got us up to 28.6 degrees Celsius. So we've done this experiment two ways. We did part one, where we had endothermic reaction for enthalpy of solution. And now we've done it backwards. We unsolutionized, and in this case it was an exothermic reaction. Now, not all enthalpies of solutions are endothermic. There are quite a few that are exothermic. But these two were a really neat example of things. So there we go.